SwayamPrabha. Digital India. Educated India.
सहनावतु सहनौ भुनक्तु सह वीर्यं करवावहै तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
So, welcome to lecture number 3 on our ongoing series on mechanical measurements. The topics I am going to cover today: error estimation, and this will be basically discussion on statistical principles, and broadly speaking they will be given without proof, but I will give some physical explanation of the for the plausibility of the proof of the results which I am going to give without proof. The subsequent topic which I am going to look at in more detail is a question of propagation of errors, and in both the cases I am going to give some examples, one example in each, to bring out the meaning of what I am going to talk about. And if time permits, I will introduce regression analysis as the last topic. I am not so sure that there will be enough time, but if some time is there, we will do that one. So, the question which I am going to look at is going to appear in the following fashion. Suppose I am doing a certain experiment. I have set up the experiment and I am going to repeat the experiments. Physically, it is not possible to do the experiment a large number of times, and therefore, I will be collecting a certain set of data. That means, I will repeat the experiment maybe a couple of times, a few times, and I am going to replicate data from these measurements. Suppose I repeat the measurements n times, that means that I am going to set up the experiment at a particular configuration, and in that particular configuration I am going to not change the variables, I am going to make the measurements repeatably. The idea of repeatable measurement is to get at the statistics of what is going to happen to the errors which are associated with the measurement. So, what I can do, or what one can do, is to do this replication of data n times, n data collection at a time, and we will call it a set, and then I will do the experiment again repeat the experiment n times and get a set which I will call as set number 2. So, in principle I can collect a large number of sets, maybe m sets. So, the question now is the first set, the second set, and so on up to the last set I have collected, each by itself contains a certain number of data n. So, each set of data has got its own mean. So, let us just look at what we have. Each one of them, that means I am talking about the set here, each one of the set has got a mean and a variance. Variance represents the position of that particular set. So, the question is there a relationship between the mean and the standard deviation of the means? That means I am measuring by collecting data in the form of sets, each having n data points in the set. I am measuring again and again. So, if I measure m such sets, I will get m means. There will be m means, and each one of them will have its own precision or variance. therefore, m variances I am going to have. All right, I have got several means and several variances. So, what I will do is I will just indicate how it is going to be done on the tablet. So, what we have is repeated data n in each set and we have m sets. I am using capital M for the number of sets. So, each set will have its mean and its variance. We will refer to each one of these sets also as a sample. This is a sample. So, I have m samples capital M of number of samples of replicated data or replicate data or repeated data, each with its own mean and its own variance. That means that sample has got a mean, we can indicate by m subscript say s as the sample mean or the variance as sigma squared for the sample. So, ms and sigma s squared. Now, suppose the data collection involve, let us say, capital N measurements. This n is the total number normally or usually greater than n. Suppose the data collection involved capital N number of measurements, which is very large compared to n. Of course, I have not done this. I am going to assume that I am able to do it or repeat the data a capital N number of times, which is a very large number. Then what I will get is shown in the next slide. So, here I have total number of measurements capital N. I will refer to this as the population. The terminology is all borrowed from statistical analysis, and when we talk about the sample, which is got its own mean and variance, and when we refer to the population here, the samples were just a few of the data which are contained within n. So, samples are drawn from the population n. So, I can assume that the population itself has got a mean. So, the mean of the population, I will give the symbol m. This is the mean of the population. The symbol m represents the mean of the population, and let me assume that the population also has got a variance which I will call as the sigma squared. If I do not use any subscript, it means that represents the population. So, the question we are going to ask is, what is the relationship between, so we have sigma s squared and ms, we have m and sigma squared. What is the link? Between these two? That is the question I am going to ask. So, the thing I am trying to describe is what is called sampling theory. I am not going to give any proof for any of the things I am going to describe today, because that is going to take too much time, and in this course we do not just have time to describe in great detail. But nevertheless, we are interested in the outcome of sampling theory, because it is going to be a very important input when it comes to estimation of errors, which we are going to be constantly doing in our measurement process. Whatever I have described in words now, I can also describe in the form of a graph. So, let me just draw a graph here. This is the axis of the quantity we are measuring. Let me just call it as x, and I am going to measure it again and again. Suppose I made, as I said, a sample. Let us say n is equal to 5. I make the measurement 5 times and I get a sample, and I can characterize this sample by its own mean and its variance. So, let us say this is the mean of the sample, mean 1, and if I were to indicate the variation of that, I will probably get something like this. This is the distribution, which has got a variance given by sigma 1 squared. Okay? I will repeat it, and next time I do again another experiment where I am going to measure it an equal number of times, and I will get a separate different mean, and it will have its own sigma 2 squared. So, this is the like that. So, m1, m2 are two samples, and each one has got sigma 1 squared variance for the sample number 1, sigma 2 squared is sample for the variance for the sample number 2. So, I can do it any number of times. For example, I can show one more, or generally I can show this is mi, and it has got sigma I squared. So, the question I am asking is, suppose the sample, the mean of the population is m, this is for the population, because I have already introduced the notation earlier, and it has got its own distribution. This is sigma squared. So, I want to know what is the link between this and these quantities, and I want to see what is the link between these quantities, that is m1, m2, mi, etc. I am going to find out what is the relationship between them and the mean of the population, and I am going to also look at the variance of the entire population and the variances of each one of the samples. Why are we concerned with this? Imagine you are conducting the experiment, and maybe I am going to just do once, I am going to just collect one sample. Let us say this is sample, m2 is the only one sample I am going to collect, and it will have its own mean and it will give a variance. Now, what I want to get at is the value indicated here, and I want to find out what is the precision if I were to repeat the measurement again and again a large number of times. So, it is a very important question from measurement theory and practice, and therefore, we are concerned with this question of linkage between these two. So, what I am going to do is to look at this question, and that is done in the subsequent slide. So, I am just repeating whatever I have said earlier. So, we have a n, the total number of data in the entire population, and the mean of all the sets we can show which I call as m without any subscript, will be nothing but the population mean, which I used as the capital M earlier. That is, the mean of all the collected data taken as a whole will be actually equal to the population mean. So, that is number one observation. The second observation is, if you look at the variance of the population, I can define it in this particular fashion using the definition which we have given earlier in our earlier lecture. Sigma squared for the population is equal to sigma I equal to 1 to capital N, where n is the total number of xi minus m whole squared divided by n. This is the definition. Now, let us look at the population values. So, let the variance of the means be given by sigma m squared. This is the variance of the means. The means are distributed in their own way, m1, m2, etc. These have their own mean and their own variance. Regarding the mean, I have already described in the earlier slide that it is the mean of those means must be equal to the population mean. But now, let us look at the variance of these means. So, if I indicate by the symbol sigma m squared, we can show again, this is without proof I am giving, that sigma m squared, the variance of the means is given by a formula n capital N minus n divided by small n into n minus 1 sigma squared. That means that the variance of the means is related to the population variance. So, sigma m squared is related to sigma squared through a factor. If I look at this factor, you see that it contains n minus n in the numerator. In the denominator, I have got two factors, n, the lower case n, which is the number of experiments performed in each sample, and n minus 1, where n is the number of total number of experiments. So, now what I am going to do is, I am going to look at what is going to happen in actual practice. That is shown in the next slide. So, if n is very small compared to n, that means that I am doing the experiment only a certain small number of times, which is lower case n. That means I am going to take only one sample. Okay. N equal to I equal to 1, 2, 3, etc. I was talking about. I talked about several samples. I am taking only one of those samples, because that is the only one which is available in our measurement. We have made only one measurement containing a sample, let us say small n number times of times measured. So, I have one set with a n data available in that set, and this is much smaller than the total n which should have been done if I wanted to understand totally what was happening to the errors. So, the error, the above relation which is given in the previous slide can be, which is given here, n minus n. So, I am going to take n outside. So, it becomes 1 minus n divided by n, the ratio of number of data in a sample divided by the number, total number, divided by, actually this total number is nothing but the number of m such samples multiplied by n, that will be the number. So, in the denominator I have got n, this n I will take out, it will give you 1 minus 1 over n, and those two n's have cancelled, and therefore I got this. Now, if I assume that n is very small compared to n, that is the assumption we have made, which is what is possible practically. You see that this factor is very small compared to 1, this factor is also small compared to 1, therefore, these two can be neglected, and therefore, I can see that approximately sigma m squared, this is the variance of the sample I have collected, is equal to sigma squared, the variance of the population, divided by n. This is a very important formula, because knowing the variance of the sample we have collected, we can say something about if we had, or had we repeated the measurements a very, very large number of times, what would have been the results. So, you see that the 1 over n is coming into picture. Sigma squared by n is sigma m squared, or if you want to find out what is the variance of the population, sigma squared equal to n times sigma m squared. So, you have to multiply sigma m squared by a factor of n to get the variance of the sample. So, with this background, let us look at the next question which I am going to ask. So, the next question is about the sample and its own variance, that sigma m squared, which I showed in the last slide. So, if you go back to the slide, you will see sigma m squared is the variance for that particular sample. I am going to slightly change the symbol and I will call the sample variance from its own mean. MS is the sample mean. I will call it a sigma epsilon sigma E squared. This E symbol is used as an estimator. I am going to use the sample variance as an estimator or estimate for the mean of the population. So, the question is, how is it related to the population variance? That means sample and its variance. We have one sample containing some number of measured values and its own variance I have calculated. I want to find out how this is related. That means that how sigma E squared is related to the population variance. Actually, again without proof, I am going to show the expression sigma E squared, the value which I calculated from the sample, one sample and the variance of that sample is given by capital N into n minus 1 divided by lowercase into n minus 1 sigma squared. Again, if I take this n outside, this becomes 1 minus 1 over n, and you see that the small n being very small compared to capital N, I can neglect that term, and therefore, I can write this as sigma squared into 1 minus 1 over n. So, sigma squared into 1 minus 1 over n equal to sigma epsilon E squared, or you can see also that sigma squared equal to sigma E squared into 1 minus 1 over n. It is a factor which is coming. If I had not taken into account the fact that it is a sample variance is different from the population variance, I would have been ignoring this 1 over n quantity. This 1 over n is the quantity which is going to be extra. So, going back to that expression which I gave here, sigma E squared equal to sigma squared into 1 minus 1 over n, I am recapitulating the definition. The last expression may be written in a different form, more explicit form. I just want to make sure that we understand what we are doing. I have got a certain number of measurement xi, I equal to 1 to small number of small n. I am going to take into calculate the variance. I am translating this expression here, sigma E squared equal to sigma squared into 1 minus 1 over n to this definition here. So, sigma E squared is equal to sigma 1 to n, because that 1 minus 1 over n is coming, 1 minus 1 over n is nothing but n minus 1 divided by n, and that n will cancel off with the number of summations in the numerator, and therefore, n minus 1 is what I am going to get here. That n will cancel off, there will be one factor n in the numerator and the denominator which came from there. Therefore, essentially what I have is the variance which estimates the error in a single sample is given by sigma 1 to n xi minus ms, the sample mean whole square divided by n minus 1. If you recollect, previously we had n here in the denominator, but now I got n minus 1. So, the question is, of course, we have without proof we have derived this relationship based on sampling theory. So, I would like to just make it physically plausible, and therefore, what I am going to do is I am going to look at the I am going to look at make a simple note on the board, so that we can understand or give a physical explanation for the thing. So, let us look at the physical explanation. So, to recapitulate, we have xi I equal to 1 to n, and the mean ms is actually sigma xi 1 to n divided by n. There is no confusion here. But however, when I want to calculate the sigma E squared, I am going to write it as divided by n minus 1. So, the physical argument is like this. So, in calculating the mean, or estimating the best value. This is also the best value, if you remember, we have already proved this earlier. So, the best value is nothing but ms equal to sigma I equal to 1 to n xi by m xi by n. What is this best value? This best value is based on the measurements available here, xi I equal to 1 to n. And when I am calculating this, I am using ms, which is calculated using this formula here. So, in calculating this ms, I have used one information or one unit of information based on data. So, I have already used one information based on data in the form of ms. Therefore, when I am evaluating sigma e squared, I have only n minus 1 information with me. So, we call this n is the degree of freedom to start with, or we will call this also as DOF, degree of freedom, because we will be using this terminology again and again. And now, you can say that this is the degree of freedom available to me. In other words, the error estimator has to take into account that one piece of information has already been derived based on the sample, and therefore, to that extent the sample is already used, and therefore, the number of degrees of freedom, which was n, that means that n samples were available, n data were available. It is as though n minus 1 data is only available now to me, because one information has been obtained using that data. And we can in fact generalize this. We can in fact generalize this to a case where, let us say, I am measuring data which is in the form of a relationship between two different quantities. Suppose I have a derived quantity y, this is the derived quantity, x is the primary quantity. The idea is now to generalize what we have said till now to measurement of two quantities which are related to each other. So, when I measure x, I can find out y, and this can be symbolically written as y equal to y of x, and I will write a set of parameters, let us say a1, a2. So, we can have number of parameters, we can have p, number of primary measurements, that means that number of measurements n, that is the sample I am talking about, number of parameters p. In the previous case, p was exactly equal to 1. I just calculated the mean of the values. P was one single parameter which was derived by using the n values. In this case, I am going to use the information given to determine p number of parameters. Therefore, degree of freedom is equal to n minus p. Earlier case it was 1, because I got only y was the mean actually. In the previous case, y was nothing but the mean of the values. Y could also be something else which is dependent on the x. For example, I may want to determine the square of the x. I may want to find out what is the estimate for the square of the x. So, I will be getting another parameter which will be square of the parameter. Therefore, each time you are going to use the data to obtain some parameter which characterizes it, I will be losing one degree of freedom, and therefore, if there are n parameters as shown here, I am sorry, p number of parameters as shown here a1 to ap, then the number of degrees of freedom lost is p, and therefore you get a degree of freedom n minus p. Therefore, when you use the variance formula, you have to divide by n minus p, and therefore the sampling theory shows or says that if you evaluate a number of parameters p with a number of n number of data available after repeated measurement, you are going to the variance is actually bigger than what you would think. The bigger it will be bigger than what you think. That is what you will see. In fact, I am going to take an example which clearly indicates this, and in fact I am taking an example which was taken in the previous lecture. The same example where I measure the resistance of a certain resistor again and again, and the data is exactly the same, no difference, but I am going to reinterpret now in terms of what we have learned from sampling theory. So, with the resistance of a certain resistor, if you go back to this slide, you will see is measured, repeatedly obtain the following data. Number represents the number of experiment number, in this case 1, 2, 3, etc. And in each one of these I have measured the resistance as 1.22, etc. and I have already discussed this example, therefore we need not go through all of them. So, 1.22, 23, 26, 21, 22, 22, 22 and 24 and 19, these are the individual values of the resistor obtained in the experiment. So, what is the best estimate? Of course, this best estimate already we know is nothing but the mean of all these values, and that does not change from the previous lecture to this lecture. But what is the error with 95% confidence? That is the one which is going to change. So, best estimate is the mean, and it was also obtained in the last example. Example 1 contained the same numbers. In fact, I have taken the slide from there in the first lecture, the second lecture. So, the value of R bar is 1.22 kilo ohms, and now I have changed the symbols here. I have used the estimator sigma e, as you can see here sigma e is the estimator, and then sigma e squared is now 1 over n minus 1, n is 9, 9 minus 1 is 8, 1 over 8 of sigma 1 to 9. Instead of 1 over 9, I have taken 1 over 8, which is 1 over n minus 1, sigma 1 to 9 Ri minus R bar whole squared. R bar is nothing but your sample mean in the previous terminology. So, Ri minus R bar whole squared, this gives you slightly more now, 3.75. The earlier case it was 3.33. It has increased to 3.75 10 to the power of minus 4, and therefore I can obtain the this must be this is wrong here, it should be sigma e is actually 0.02 kilo ohm. So, this is sigma e equal to square root of this number 0.02, it is 0.019 which I am rounding out to 0.02, and the previous case I had also rounded off to 0.02, but this was smaller than this. Therefore, the final answer does not change, the final answer does not change. 1.96 times sigma is roughly equal to 0.04, actually it is 0.036. In the earlier case it was slightly smaller than this. Therefore, you see that the estimated value of the error is larger when you take into account the results from the sampling theory. So, just to round off, what we should do is, in the future whenever we give an example, we will use the results derived from sampling theory. That means, we are going to divide the variance by the number of degrees of freedom, but not number of samples, number of measurements. It will be n minus p, where n is the number of times we have repeated the measurement, p is the number of parameters we have estimated. In fact, when we go to regression analysis, it will become more clear as to what we mean by the number of parameters. But right now, we shall remember that the division is by n minus p, but not n itself. That means that the error is actually larger than what you would imagine. So, now let us look at the second thing which we mentioned in the first slide, the question of propagation of errors. Let me just briefly explain what is happening here. A derived quantity q, which is shown by the symbol capital Q, is estimated based on the measurement of primary quantities A1, A2, AM here. The number of parameters and number of primary quantities measured is A1, A2, etc. AM. Each one of these is repeated again and again. That means that A1, A2 up to AM, these are all measured again and again, and we have some idea about the statistical variation of these quantities also. And what I want to know is to find out how the statistical variations in the quantities A1 to AM are going to affect the statistical variation of the Q. So, the primary measured quantities have measurement errors which are already characterized, given by the respective variances sigma I squared. A1 has got sigma 1 squared, sigma 2 squared corresponds to the error in A2, sigma m squared will correspond to sigma variance in the this particular parameter which I am measuring. Okay. Sigma 1, sigma 2, etc. are the standard deviation of the measurement of each one of these quantities A1 to AM. Now, the question is, what is the best estimate for capital Q and what is the variance of Q? So, the question is very simple. I have got A1, A2, etc. measured again and again, and therefore, I should be having the mean values of A1, mean value of A2 and mean value of A. Okay. That means that these values of these, after doing them in a large number of times or doing the measurements a large number of times, I have got a mean value for A1, mean value for A2 and so on up to AM. And I also have, as given here, the variance for each one of the quantities. So, the propagation of error means there is a certain error in the value of A1, how is going to propagate or make itself felt in the case of Q. There is a certain value of certain error in A2, how is it going to affect the error in Q? There is a certain error in AM, how is it going to affect this? So, all the error in each one of these quantities is going to influence or affect the measured value of Q, and therefore, this process of the error migrating or moving or shifting or propagating from here to here, from here to here, here to here is what is called the propagation of error. So, what I will do is, I will use the board to work out the details of the relationship between the error in the measured quantities or the primary quantities and the error in the derived quantity. So, the end product of this exercise would be a formula which will help us calculate the error in the Q. Okay. Let us just recapitulate what we have done. So, we have measured a quantity Q which actually depends on several primary quantities A2, A1, A2, etc. AM. I also have A1 bar, A2 bar, these are also known. Let me just write it here, known. Also this is one. What else is known? We also know sigma 1 squared, sigma 2 squared, sigma m squared. How do we know these things? We know 1 and 2 from repeated or replicate data. I want to digress a little bit here and talk about these errors sigma 1 squared, sigma 2 squared and so on. In actual practice, what is going to happen? That is why sometimes it is confusing that I say something mathematically, then we go to the laboratory and I do something else totally different. So, this is a problem for which there is no solution, only a little bit of thinking about it and understanding what is going on would probably help us. In practice, what happens is that I am not even going to repeat the measurement again and again. Sometimes I may take only one reading or maybe 2 or 3 readings at the most, and then I would like to find out what is happening. But in making the measurement, I am making use of some instrument, and we know that the instrument can resolve some, basically a certain smallest quantity I can measure. It can resolve between 2 values which are only that close and no closer. So, sometimes what we do is, even though it may not be mathematically correct, sometimes what we do is, instead of using the errors obtained from replicate data, we may use the maximum error due to just the instrument itself. The instrument itself cannot resolve a certain quantity to better than some value, and therefore, the resolution of the instrument itself may be used sometime for the estimation of these errors. So, sigma 1 squared, sigma 2 squared, etc., sigma m squared may be taken from the behavior of the instrument. This is not strictly correct. It is not like doing the experiment again and again and understanding the statistics. We are replacing the statistical behavior of the error by looking at the errors introduced in the measurement process due to the limitation of the instrument. This may be justified in a physical sense, that the measurement process involves the process of taking a reading. You may take the reading yourself using your eyesight, or you may ask somebody else to take the reading, or it may be even gathered by a data acquisition system. The measurement process can be anything. In each one of the case, there is a certain minimum resolution or minimum smallest quantity which we can resolve, and we cannot resolve better than that. And therefore, we can say physically that probably that is the kind of error we are going to introduce in the measurement. Therefore, I am going to replace the statistically determined errors sigma 1 squared, sigma 2 squared, etc., by the errors due to the measurement process, which involves a certain instrument and certain process of getting the data, and there is an error introduced in that which is considered as accidental. So, it is a certain approximation involved in this, certain hand waving is involved, but I think we all try to do that all the time. So, with this background, what is the question I am asking now? I want to find out what is sigma q squared. So, to understand this problem, let us indicate how we estimate the best value for q. So, for determining the best value, I am going to say QB. I will say QB is the best value is nothing but QB based on A1 bar. That means, I am going to use, these are all the best values. Best values for the A's. There is no need to prove this, because we know that A1, A2, etc., the mean values are the best values for these. So, I am just assuming or guessing or claiming that the best value of q is nothing but the value obtained by using the best values for each one of these measurements. So, this will be, there is no proof for this, we are just asserting this, and this may be any functional relationship. This is a relationship QB related to A1, etc., through some mathematical expression. Okay. Now, let us assume This is a very important assumption. Sigmas are much smaller than the A's. Most of the time we can justify this. We assume that the errors in the measured values are not very large compared to the values of the measured quantities themselves. This is a very important assumption. If they are not, then whatever we are going to derive is not going to be applicable, as simple as that. So, with this assumption, I am going to assume that the perturbations sigmas are like perturbations, and therefore, I can use a Taylor expansion to decide what is going to be the perturbation in the value of q. So, if I take q minus qb, qb is the best value, which is obtained by using the values of A's given by A1 bar, A2 bar, etc. And now I am going to perturb this value, because whenever A1 is perturbed, q will be perturbed from the value of qb. When A2 is perturbed, q will be perturbed from the value of qb. Therefore, this can be written as a Taylor expansion. So, this is a Taylor series. Of course, Taylor series is valid for infinitesimal changes, and that can be written as sigma I equal to 1 to m partial of q with respect to the A in fact, I am showing only the first order terms, of course, plus terms of order delta Aj squared. So, these are the perturbations. These are the partial derivatives, because you notice that the function q is a function of several variables, and therefore, the Taylor expansion will contain derivative with respect to each one of these variables in turn, and therefore, you get partial derivatives. If you write this for a single variable, you would not get a summation here, and these perturbations are the ones which are given to us. We will see how it is incorporated later on. So, these are partial derivatives, and we also refer to them as influence coefficients. The reason why they are referred to as influence coefficients is, if delta Aj is some perturbation, q minus qb will be perturbed by a product of delta Aj multiplied by this coefficient. This is the dou q by dou Aj. So, the derivative is enhanced or multiplied by the the perturbation is multiplied or enhanced by the magnitude of dou q by dou Aj. The larger the influence coefficient, the larger the magnification, and therefore, the larger the influence of Aj on q. So, that is why it is called the influence coefficient. Now, what we have here is q minus qb equal to this, and what I am interested in finding out is the variance of the q, and we will just use the definition of the variance, which is given by sigma q squared must be equal to sigma q minus qb whole squared divided by the number of times the measurements were done. So, I will say sigma over n for conciseness, and this can be written as sigma. I will just keep the sigma outside, this is the exponent number. So, I can say I equal to 1 to n q minus qb whole squared. I will write that expression we have derived earlier, q minus qb equal to sigma over the j's. So, j equal to 1 to m dou q by dou a j multiplied by delta a j whole square. So, we have two sums. One is the number of times the measurements have been done, the other one is over the number of quantities a j which are involved in the process. And the question is, how do we evaluate the influence coefficient? Evaluate at a bars dou q by dou a j will be evaluated, because that is the point which is known. The derivatives are all evaluated at the best value. So, I am going to replace the derivative also at the best value. That means that dou q by dou a j are going to be evaluated at the set of values a 1 bar, a 2 bar, etc. up to a m bar. Now, this if I square this what is shown inside this I am talking about this quantity. This square will involve two types of terms. It is like x plus y plus z whole squared is x squared plus y squared plus z squared plus 2xy plus 2yz, etc. So, there are two types of terms. One type of term which involves the square of individual terms, the other one involves the products of terms. So, let us look at these two types of terms. So, the square term, square will involves for example dou q by dou a j whole square. This is one. Second one, it will involve delta a j, delta a k. This is certainly just simply a coefficient, certain number. When I evaluate at the best point, this is some number, some quantity, some value. These are the individual errors. Now, I am going to make the following assumption, that the error in delta a j is not related to error in delta a k. That means that a j and a k are independent of each other. For example, in practice, I may use a voltmeter to measure the voltage, a k may be a voltage. I may be measuring a length measurement using a vernier caliper to measure delta a j. So, how are they going to be affected by each other? Nowhere. The error in this and this error, so these errors are independent. So, what will happen if I have a product of two quantities which are not related to each other is that this will tend to 0 as n tends to a large number. If I measure again and again, the product of two quantities which are not related to each other will tend to 0, whereas this is of course a square quantity, this is always positive. Therefore, with this we can see that what we are going to do is to have q minus qb whole squared will be equal to this will be I think I have to show one more sigma here. 1 to n the number of experiments, and this will be, and therefore I can put a flower bracket here, and this is the square of the error, and if I divide this by n I should get the variance. So, I have to derive by n. I think I will divide it by the n on the right hand side, not on the left hand side, divided by n. So, what is this quantity now? This whole thing, dou q by dou aj delta aj whole squared. I can take one of those terms. This will be dou q by dou aj to delta aj square, and actually this is also a summation sigma j equal to 1 to m 1 to n divided by n, because this n is coming from there. This is nothing but your sigma a1 squared or sigma 1 squared. So, you see that all I have to do is to, and in fact I can relate it to sigma q squared, and therefore I can say that sigma q squared is equal to sigma I equal to 1 to m sigma q squared equal to I equal to 1 to m dou q by sigma j whole square. This is called the error propagation formula. I think we will have to stop here, and we will resume from here in the next lecture. We will take an example which will be given at that time, and then move on to the question of regression analysis as a subsequent or a sequel to this detailed look we are having at the question of errors in measurement, how to characterize them. So, we have come quite far from where we started. We now understand the sampling theory, its results are known to us, and then we are able to look at the propagation of errors. And this legitimately, the next part is to look at the relationships, that means regression analysis, which is a description of this whole thing. Thank you.